So next term is heat transfer. That is second term from energy interaction. We have beautifully seen what is work transfer. Now it is the turn of heat transfer. According to thermodynamics, heat transfer is defined as the energy interaction due to temperature difference. Consider that I am having two objects. Let this object is having high temperature than this one. If I am keeping these two objects together, there will be heat transfer from this object to this object, and as a result the temperature of this body will be increasing and temperature of this body will be decreasing, and finally both of them will achieve a same temperature, and thereafter there won't be any heat transfer. Okay, and in everyday life also we are using the term heat or heat transfer. Let's see an example and see how a common man will be interpreting that result, and a thermodynamic student like you will be interpreting that result. Okay, let's see. I am inserting a high temperature coin to this water. This water is cold water. As a result, the temperature of water will rise, right? And let's see how a common man will be saying about that experiment. The common man will say that heat has been transferred from coin to water. As a result, the heat content of water has increased. Note the word heat content of water has increased. But you will be saying that heat has been transferred from coin to water, and as a result, internal energy or thermal energy of the water has increased, not the heat content, right? Because heat cannot be stored inside a system. That's how we are defining heat transfer. It will be having meaning only when there is a process is happening. The moment the process is over, the meaning of heat transfer vanishes. That means the meaning of heat transfer will be there only when there is a process is occurring. So here clearly we have seen that when we insert a coin to water, there was a process was occurring. As a result, the heat was transferring from the coin to water. Once they both achieve same temperature, the process is over. Thereafter there is no heat transfer. The main point you have to understand is that heat cannot be stored inside a system. It is thermal energy or internal energy. That's what we are storing inside a system. So heat transfer is not a property. It cannot be stored inside a system. It's not a property. Similar to work transfer, it is also a boundary phenomena. If it is not crossing the boundary, it doesn't have any meaning. So heat transfer is not a property, and this is not it is a boundary phenomena, right? And let's quantify the term heat transfer. Consider two beakers of water. One is big beaker, and let this contain 1 kilogram of water, and this is containing 10 kilogram of water. Okay, and initial temperature was 20 degrees Celsius. Here also initial temperature is 20 degrees Celsius, and the both are achieving a final temperature of 40 degrees Celsius. Okay, both are achieving 40 degrees Celsius, and in order to achieve the 40 degrees Celsius in both cases, I had to transfer some heat, right? I had to give some heat, then only there will be rise in temperature, right? So can you tell me in which case I have to supply more heat? In which case there should be more heat transfer, therefore we can have the final temperature of 40 degrees Celsius. It's clearly this case, right? Since it is containing 10 kilogram of mass, I will have to give more heat transfer, then only I will be getting 40 degrees Celsius. So heat transfer Q is directly proportional to mass. Am I right? Now consider two beakers. One is having 1 kilogram and initial temperature is 20 degrees Celsius, and second beaker is also having 1 kilogram and initial temperature is 20 degrees Celsius. Okay. In this case, let this final temperature be 80 degrees Celsius. In this case, the final temperature is 40 degrees Celsius. So, can you tell me in which case I might have given more heat? This case or this case? Both are having same mass, but this in this case, the final temperature is 80 degrees Celsius. Here it is only 40 degrees Celsius. So can you tell me in which case I might have given more heat? This case, right? Because the temperature difference is very high. So I can directly write heat transfer directly proportional to temperature difference, or heat is directly proportional to m into delta T. So we know that by using a proportionality constant we can equate the heat transfer and these terms. So I can write Q equal to m into, let the proportionality constant be C, and delta T. So I can say that heat transferred in any case is equal to mc delta T, where C is called specific heat and it is having a unit of kilojoule per kilogram Kelvin. Let's see how we are getting that. So from this equation I can write C is equal to Q by m into delta T. Am I right? Now what is the unit of heat? It is nothing but a same form of energy, right? So it will be having a unit of kilojoule, and mass is having a unit of kilogram, and temperature is having a unit of Kelvin. So it will see specific heat is having a unit of kilojoule per kilogram Kelvin, right? And what is the physical meaning of specific heat? Specific heat gives the how much heat, how much energy substance can absorb. Heat carrying capacity, that's how we used to say. That means this plastic will be having specific heat carrying capacity, and the water inside this glass will be having some other specific heat capacity. That means for having unit rise in the degree Celsius for unit mass system, the heat supplied required is more in the case of water than this case. In this case, water is having a specific heat of 4.18 kilojoule per kilogram Kelvin. That means we have to supply 4.18 kilojoule for a 1 kilogram system of water to rise to have a temperature difference of 1 degree Celsius. But in the case of plastic or any metal like iron, it will be very less compared to water. That's why we are using water as the working substance in thermal power plants, because it will carry a lot of heat than any other substance. Okay, so specific heat implies the heat carrying capacity of any material. Okay, let's understand the term specific heat in detail. Consider that I am having 1 kilogram of substance and I am raising the temperature to 21 degrees Celsius. The initial temperature was 20 degrees Celsius. So the delta T term is nothing but 1. What is m here? 1, right? So C will be equal to, this is coming to 1, this is coming to 1. C is equal to Q. So specific heat is defined as the amount of heat required to rise the 1 kilogram mass system to have a temperature of 1 degree Celsius. Okay, is that clear? That means how much heat we have to supply to have 1 degree Celsius rise in a unit mass system. That's what specific heat is meaning. And there are two types of specific heat. And first one is specific heat at constant pressure, and second one is specific heat at constant volume. Let's see what are they.